Hi everyone, my name is Nangwin. Today I'm going to talk about cryptography and RSA encryption. What is cryptography? Cryptography is a process of encoding messages with a cipher, turning the message into encrypted code that need to be decoded. Cipher transform the letter, turning them into other letter or even numeric value when the message is encoded. The encoded message is locked with a key or password. The message is unlocked with the inverse of that key, allow it to be read in plain text. But what exactly does it look like? Let's look at some simple example. Here is our alphabet with numeric relation. Message, a secret. Using our alphabet with numeric relation, we will turn A into 1, dash into 27, S to 19, E to 5, C to 3, R to 18, E to 5, and T to 20. We will then get our message into vector format. This is our lock to lock up the message, encoding it. Our vector transforms into 2 by 1 matrix. To encode the message, we will use the formula y equals xa. Y stands for encoding message, X stands for original message, and A is our key matrix. By multiplying a key matrix and the original matrix, we will get the new set of matrices that have no meaning. This is how it looks like in comparison. Now that we have these numbers, how do we decoding them? Ideally, there are two keys to lock and unlock the message. Encoding and decoding. A inverse is another key, which is unlock key. Let's find the original message by multiplying the unlock key with the matrix that have no meaning. Then we will get our original message. With the new code, we then use the alphabet with numeric relation to turn it back into the readable message. How does this method apply to the real world?
Hi, my name is Lydia and I will be talking about RSA encryption. This type of encryption is typically used to prevent data theft. RSA encryption takes years, maybe even hundreds of years to crack, even with a supercomputer. Because of this, hackers don't have the time or the patience to wait around to steal the data. Even if the data was stolen, the encryption makes the data impossible to read because the hacker won't have the proper keys to decrypt the data. What data is at risk? All of it. Here are just a few examples. Emails, bankings, laptops. If it connects to the internet, it can be compromised, said by Lieutenant Bratton, U.S. Army Cyber Command. The earlier slides use symmetric encryption, however, RSA uses asymmetric encryption. This means that the sending and receiving party will not have the same information. How does it all work? Let's look at an example. First of all, we need to determine a few values. We need to calculate the value of n, which is equal to an arbitrary prime number times a different arbitrary prime number. Then we find the modulus of the product of these two prime numbers. We call this value the public coefficient. We won't really need to know about modular math or phi of numbers because the computer does it all for us. Now we need to calculate e, the public key exponent. E can be any number within the range of 3 and phi of n. We choose 3 because it's the first reasonable prime number. Then we will need to calculate d, the private key. We calculate d with this formula. Here's how RSA is used. The first use is encrypting with a public key, and then we decrypt with a private key. Let's say Bob is sending an encrypted message to Alice. The sending computer goes through this formula and creates this ciphertext C. Alice gets the message. The receiving computer receives C and puts C through a formula and results in M, the decrypted message. This is how she can read it. Here's a visual diagram. Bob is chatting to Alice online. Bob sends a message. Jill is snooping on Alice and Bob by attempting to intercept the message. However, Bob and Alice are using RSA encryption. What will Jill see? The next few slides are numerical calculations the computers go through to encrypt the message. Alice's computer generates a public key. Alice's computer then finds phi of n. Alice's computer picks some value of e. Then it will generate a private exponent d, which is her private key. All of these values will be private except for n and e. These numbers will make up her public key. Alice's computer will send this public key to Bob. Bob locked his message with Alice's public key using this formula. Going back to the visual diagram, Jill intercepts the message. Can she figure the encryption out? Jill has the intercepted message that reads 1394. Jill is missing two whole variables. All she knows is Alice's public key. Jill can only figure out the encryption if she can find phi of n. However, to find phi of n, she will need the prime factors that generated n, which she does not have. If Jill can factor n, which in practical use is hundreds of digits long, and if she wants to find out this one message, she could be looking at factoring for a long time. Going back to the visual diagram, Alice receives the message from Bob. Can Alice figure out the encryption? Alice gets the message from Bob. She has D, which is derived from E and modulus n, seen in the previous slides. The receiving computer uses a formula to decrypt the message. The computer does some calculations. Alice has all the right tools to unlock the encryption, and thus she can read the original message. Alice replies to Bob using Bob's public key, and this complicated process starts again. Bob and Alice chat in confidence, knowing that their little chat is safe. And with Bob sending a message back to Alice, Jill is still clueless about the conversation between the two. This is how RSA encryption works. Here are some of the sources we used. Thank you.